Hello, young chemists. Let's start with a mystery. Why does our blood look red, and why do plants wear green? The heroes behind the curtain are coordination compounds. These form when a central metal ion, like iron, copper, or cobalt, bonds with surrounding ions or molecules through coordinate covalent bonds. Think of them as Lego sets. The metal is the central block, and ligands are the pieces snapping into place. Together, they build strong and stable structures. And they're everywhere. Hemoglobin carries oxygen in your blood, chlorophyll captures sunlight in plants, vitamin B12 keeps you healthy, and industries use coordination compounds in catalysis, electroplating, dyeing, and even designing life-saving drugs. Truly, coordination compounds are chemistry's hidden superheroes. Now let's travel back to meet Alfred Werner, the Sherlock Holmes of coordination chemistry. He explained that metals show two types of valencies. First, the primary valence, which is ionic and satisfied by simple ions like chloride. Second, the secondary valence, formed by coordinate covalent bonds with molecules like ammonia or water. He also gave us the idea of the coordination sphere, that's the central metal ion plus its attached ligands. And the number of attached ligands, called the coordination number, decides the geometry. 6 ligands usually give an octahedral shape, while 4 ligands may give tetrahedral or square planar. Werner's theory was like laying the foundation stone of a skyscraper. Everything in modern coordination chemistry stands on it. Now, let's meet the ligands, the faithful sidekicks of metals. A ligand is any ion or molecule that donates a lone pair of electrons to the central metal ion. Some are unidentate, they hold on with one atom, like chloride ion or ammonia. Some are bidentate, like ethylenediamine, gripping with 2 atoms like a pincer. And then we have polydentate ligands, also called chelating agents, like EDTA, wrapping around the metal like an octopus. The coordination number is the total number of donor atoms attached. For example, tetracarbonyl nickel has a coordination number of 4. Hexamin cobalt, 3, ion has a coordination number of 6. Picture it like seats around a dinner table, the metal is the host, and the ligands are the guests. The coordination number is simply how many seats are filled. Next comes crystal field theory, or CFT. Imagine ligands as tiny negative charges approaching the metal ion. Their approach repels the 5 d orbitals of the metal, splitting them into groups of different energy. In an octahedral arrangement, 3 orbitals become lower in energy, called T to G, while 2 orbitals become higher in energy, called EG. In a tetrahedral arrangement, the order is reversed and the gap is smaller. Strong field ligands like cyanide create large splitting. Weak field ligands like iodide create small splitting. And here's the fun part, this orbital splitting is why complexes are often colorful. When visible light hits, electrons jump between these split orbitals, and the leftover light is the color we see. Coordination compounds are like tiny disco lights at the molecular level. Another explanation comes from valence bond theory, or VBT. Here, the central metal ion mixes orbitals to form hybrid orbitals, which overlap with ligand orbitals to make coordinate covalent bonds. In an octahedral complex, the hybridization is sp3d2. In a tetrahedral complex, it is sp3. In a square planar complex, it is dsp2. These hybrid orbitals give stable bonding. But VBT also predicts magnetism. For instance, tetrachloronickelate has unpaired electrons, making it paramagnetic. But tetracarbonyl nickel that pair up the electrons, leaving none unpaired. That makes it diamagnetic. So VBT not only explains bonding but also whether a complex will love or ignore a magnet. Here's where coordination chemistry gets creative, isomerism. Even with the same formula, ligands can arrange themselves differently. In geometrical isomerism, ligands may sit next to each other, that's cis, or opposite each other, that's trans. Optical isomerism gives mirror images, like left and right hands, that can't be superimposed. Linkage isomerism occurs when a ligand can attach through different atoms. For example, pentamine nitrocobalt chloride binds through nitrogen. Its twin, pentamine nitritocobalt chloride, binds through oxygen. Same formula, but different bonds and very different behavior. Isn't it just like identical twins with different personalities? Now let's see their real-world impact. In biology, hemoglobin, an iron complex, carries oxygen in your blood. Chlorophyll, a magnesium complex, powers photosynthesis. In industries, coordination compounds act as catalysts in electroplating metals and as bright textile dyes. In medicine, cisplatin, a platinum complex, is a famous anti-cancer drug. EDTA is used in chelation therapy to remove harmful heavy metals from the body. And in analytical chemistry, EDTA is also used in titrations to measure water hardness. So, from the air you breathe, to the food you eat, to the medicines that heal you, coordination compounds are silently working behind the scenes. So, let's recap. Coordination compounds are formed when a central metal ion bonds with ligands through coordinate covalent bonds. Werner's theory explained primary and secondary valencies. Valence bond theory gave us hybridizations like sp3d2, sp3, and dsp2. Crystal field theory explained splitting of d orbitals into T to G and Eg sets. Coordination compounds can show isomerism, geometrical, optical, and linkage. And they are vital in biology, industry, and medicine. Chemistry isn't just about formulas in books, it's the invisible engineer shaping your world. I hope today's session made coordination chemistry clear and maybe even a little fun. Until next time, stay curious and keep bonding just like our ligands and metals.